Welcome to WikiPodcast. Have you ever looked up at the night sky and just, felt that sense of wonder, pondering where it all came from?
Yeah.
How did this huge, intricate universe with, billions of galaxies and countless stars actually begin?
It's the ultimate question, right?
Exactly. So today we're embarking on a truly mind-bending deep dive into the very first moments of everything. The Big Bang.
Yep.
Get ready, because we're exploring the origins of our cosmos from an unbelievably hot, dense state to the expanding, accelerating universe we see now.
So, okay, when we talk about the Big Bang, it's more than just a single moment, right? It's the main scientific theory we have for how the whole universe expanded from that initial state.
That's right. It's the framework.
What's the big picture takeaway for someone trying to get their head around this?
Well, I think the main thing is that this isn't just a guess. It's a scientific model that actually explains a huge range of things we can observe.
Like what sort of things?
Yeah.
Things like, well, why there's so much hydrogen and helium out there compared to other elements. Or the cosmic microwave background radiation, that faint glow everywhere. And even the way galaxies are clumped together in these enormous structures.
Yeah, it's the cosmic web.
Exactly. And it's how we figured out the universe is roughly, 13.8 billion years old.
Wow.
But it's important to remember, while it's widely accepted, the very earliest moments, we're talking tiny fractions of a second, involve physics that, well, we can't quite test yet. So some parts are still a bit speculative.
Okay, so it's our best explanation, backed by tons of evidence, but with some fuzzy edges right at the start. It sounds like we need to take a trip back in time then.
Yeah, let's do that.
Let's try to imagine going way, way back to when everything was incredibly hot and squeezed together.
Okay, well, if we could really rewind the clock that far, our current physics, specifically general relativity, it points towards something called an initial gravitational singularity, right at time zero.
A singularity, so infinite density,
Yeah.
infinite temperature.
That's what the math suggests, yeah. But here's where things get, well, really wild. Our current understanding of physics actually breaks down at that point.
Breaks down how?
We know quantum gravity effects must have been dominant then. This is the Planck epoch lasting an almost impossibly short time, like 10 to the minus 43 seconds.
Unimaginable.
Right. And the temperature was something like 10 to the 32 Kelvin. In that instant, the four fundamental forces we know, gravity, electromagnetism, the strong and weak nuclear forces, they were probably all unified into one single force.
Right.
Our current models just, well, they can't describe that state.
So space and time as we understand them just didn't quite apply yet. But then almost right away, something else huge happened. Cosmic inflation. That sounds like a massive growth spurt. What was going on?
It was an absolutely incredible transformation. Around maybe 10 to the minus 37 seconds, give or take, the universe went through this period of cosmic inflation. Think of it like an exponential, completely unconstrained expansion. The universe just blew up in size by an enormous factor in, the tiniest fraction of a second.
Why? What did that do?
Well, this rapid stretching helped solve some big puzzles, like the horizon problem, why distant parts of the universe look so similar, even though they couldn't have exchanged information yet.
Oh.
And it also explains the flatness problem, why the universe's geometry seems so perfectly balanced, so
Yeah.
flat.
Right.
And here's the really mind-blowing part. Tiny, microscopic quantum fluctuations, just random jiggles in the quantum fields back then, they got stretched out by inflation.
Stretched out.
Yeah, massively. And those stretched out fluctuations became the seeds for everything we see today. Every galaxy, every star cluster. It's also when those unified forces started to split apart.
It's incredible to think that huge things like galaxies started from these tiny quantum whispers frozen in place by inflation. So after inflation, the universe kept expanding and cooling down, setting the stage for, everything else.
Precisely. As it expanded, it cooled down really fast.
Yeah.
And this led to a series of phase transitions, kind of like steam condensing into water, then freezing into ice.
Okay.
So for instance, the electromagnetic and weak nuclear forces split apart around 10 to the minus 12 seconds. Then, by about a microsecond, that's a millionth of a second, it was cool enough for quarks and gluons to start sticking together.
Forming protons and neutrons.
Exactly, the building blocks of atoms. And here's something absolutely crucial. There was this tiny imbalance. For maybe every billion particles of antimatter, there were 1,000,000,001 particles of matter.
Just a tiny bit extra matter.
A tiny bit, yeah. But it meant that after almost all the matter and antimatter annihilated each other in a flash of energy,
Phew.
this small leftover amount of matter survived. And that leftover stuff, that's literally everything we see. Us, planets, stars.
Wow. That imbalance is everything.
Everything. Then, a few minutes later, maybe 3 to 20 minutes in, the temperature dropped to about 1 billion Kelvin. Still incredibly hot, but cool enough for Big Bang nucleosynthesis.
Making the first elements.
First nuclei, yeah. Protons and neutrons fused to form the nuclei of light elements, mostly deuterium, heavy hydrogen, and helium.
And this cooling continued, right, until eventually the universe cleared up, became transparent. That must have been a huge moment, letting light travel freely.
It absolutely was a pivotal moment. Around 380,000 years after the Big Bang, the universe had cooled enough down to maybe 3,000 Kelvin for electrons to finally combine with those nuclei,
Forming neutral atoms.
forming the first stable neutral atoms, mostly hydrogen and helium. Before this, what we call recombination, the universe was this hot, dense, opaque soup, a plasma. Photons, light particles were just constantly bouncing off free electrons like light in a thick fog.
Can get anywhere.
Exactly. But once neutral atoms formed, suddenly there's nothing much for the photons to bounce off. The universe became transparent. And all those photons that were trapped, they were released, free to travel across the cosmos unimpeded. And that released light, stretched out over billions of years by the expansion of space, is what we detect today as the cosmic microwave background radiation.
The CMB. The universe's baby picture, like you said.
That's a great way to think of it. Perfectly preserved light from that moment.
So recombination was the point where gravity could really start taking over and shaping things on a grand scale.
Exactly right. After recombination, those tiny density variations we talked about, the ones stretched out by inflation, they started to exert a gravitational pull.
Pulling stuff in.
Yeah. Denser regions started pulling in more and more matter, mostly hydrogen and helium gas. Over millions and then billions of years, these regions grew. They formed vast clouds, which eventually collapsed under their own gravity to create the first stars.
And then galaxies.
And then galaxies, yeah. And those galaxies clumped together into clusters, and clusters into superclusters, forming this huge web-like structure we see across the universe.
Yeah.
And something called cold dark matter, CDM, plays a really big part here.
Dark matter. The invisible stuff.
Right. It doesn't interact with light, but it has gravity. Think of it like invisible scaffolding that provided the extra gravitational oomph needed for these large structures to form as quickly and on the scale that we observe them.
Okay, so gravity and dark matter build the structures. But then, after billions of years, something else started to kind of take charge of the expansion, something unexpected.
That's right. And it leads us to one of the biggest mysteries in cosmology today. Observations, particularly of distant exploding stars called supernovae, revealed something stunning in the late 90s.
What was that?
The expansion of the universe isn't slowing down due to gravity, as everyone expected. It's actually speeding up. It's accelerating.
Accelerating. Wow. Why?
We don't fully know why. We attribute this acceleration to some mysterious component we've nicknamed dark energy. It seems to have this sort of repulsive effect, pushing space apart. It only started to dominate the universe's energy budget after billions of years, once matter had spread out and its gravitational pull became less dominant over cosmic scales.
That's an incredible journey through time. So let's shift gears a bit. How do we actually know all this? The Big Bang isn't just a cool story, it's science. What's the hard evidence? The universe's fingerprints, as you called them?
A great question. There are several key pieces of evidence, often called the pillars of the Big Bang theory. The first one is Hubble's law and the expansion. Back in 1929, Edwin Hubble observed that galaxies aren't static.
They're moving away.
Almost all of them are moving away from us, yes. And crucially, the farther away a galaxy is, the faster it appears to be receding.
How do we know that?
We measure the redshift of their light. As space expands, it stretches the wavelengths of light traveling through it, shifting them towards the red end of the spectrum. More distant galaxies have more space between us and them, so their light is stretched, more high redshift, faster apparent recession.
So space itself is expanding.
That's the key interpretation. It's not that galaxies are flying through space away from a central point. Space itself is expanding everywhere. Now, interestingly, there's a modern puzzle here called the Hubble tension.
Tension.
Yeah, different methods of measuring the current expansion rate give slightly different answers. It's a small difference, but persistent. And it might be hinting at some new physics we haven't figured out yet.
Fascinating. Okay, expansion is pillar one. And you mentioned the cosmic microwave background radiation, the CMB. That sounds like pretty direct evidence, like an echo.
It really is perhaps the most powerful piece of evidence. It was discovered accidentally in 1964 by Penzias and Wilson. They were trying to do something else entirely and kept finding this persistent microwave hiss coming from all directions.
A background noise.
Exactly. It turned out to be the leftover heat from the Big Bang itself. That flash of light released at recombination redshifted all the way down to microwave frequencies by 13.8 billion years of expansion.
Wow.
And it's an almost perfect black body spectrum, precisely as predicted, corresponding to a temperature of just 2.725 Kelvin, barely above absolute zero. But it's not perfectly smooth.
Ah, the ripples.
Yes. Satellites like COBE, WMAP, and Planck mapped it in incredible detail and found tiny temperature fluctuations differences of maybe 1 part in 100,000.
Tiny but important.
Incredibly important, those tiny hot and cold spots are the imprints of the slightly denser and less dense regions in the early universe, the very seeds, amplified by gravity over billions of years that grew into all the galaxies and clusters we see. They're literally the blueprints.
Amazing. Okay, expansion, the afterglow. What's next? You mentioned the elements earlier.
Right, pillar 3. The abundance of primordial elements. The theory of Big Bang nucleosynthesis, or BBN, makes very specific predictions about how much of the light elements should have been created in those first few minutes.
Like hydrogen and helium?
Mostly hydrogen and helium, yeah, plus tiny amounts of deuterium and lithium. The theory predicts the ratios very precisely based on the conditions in the early universe.
And do the predictions match what we see?
Remarkably well, especially for hydrogen and helium, which make up almost all the ordinary matter we see. When we look at the oldest stars and distant gas clouds, the abundances line up beautifully with the BBN predictions.
That sounds pretty solid.
It is. There's a slight issue, sometimes called the cosmological lithium problem. We seem to observe a bit less lithium than predicted. But overall, the agreement is stunning, and currently BBN is the only theory that explains these observed abundances across the cosmos.
Okay, expansion, afterglow, the recipe. Is there a fourth pillar?
Yes, you could broadly call it galactic evolution and distribution. This is about how structures formed and changed over time. When we look at very distant galaxies with powerful telescopes, we're seeing them as they were billions of years ago, because the light took so long to reach us.
Looking back in time.
Exactly. And those early galaxies look different from nearby, more mature galaxies. They're often smaller, more irregular. This observation of change over time strongly contradicts older ideas like the steady-state model, which suggests that the universe always looked pretty much the same.
So we see the universe evolving.
We do. Plus, the way galaxies and quasars are distributed on the largest scales forming filaments and voids, that cosmic web matches incredibly well with computer simulations based on the Big Bang model, including the effects of dark matter and dark energy.
And there was something more recent, too, about gas clouds.
Ah, yes. A really neat confirmation came in 2011. Astronomers found these primordial gas clouds. They were incredibly pristine, almost entirely just hydrogen and helium, lacking the heavier elements that are forged inside stars. Untouched. Exactly. They look just like gas that would have formed directly from the Big Bang conditions before stars had a chance to pollute the universe with things like carbon and oxygen. It was like finding fossils from the universe's earliest chemical state.
Okay, the evidence seems really compelling. But you mentioned earlier, it's not a complete picture. There are still big mysteries, right? Frontiers where scientists are actively digging. What are some of the biggest puzzles we still face?
Or absolutely. Science thrives on the unknown. One huge puzzle is baryon asymmetry. Why is there so much more matter than antimatter?
Right, you mentioned the slight imbalance earlier.
Exactly. The theories suggest matter and antimatter should have been created in almost perfectly equal amounts. If they were perfectly equal, they would have completely annihilated each other, leaving just energy, just light.
No stars, no planets, no us.
Precisely. So some process, which we call baryogenesis, must have created that tiny excess of matter, about one extra matter particle for every billion matter-antimatter pairs. We have ideas about how this could happen within the standard model of particle physics, but honestly, the known mechanisms don't seem quite strong enough to explain the amount of matter we see. It's a fundamental mystery about our own existence.
Okay, that's a big one. And then there are the dark components. You mentioned dark energy and dark matter. They make up most of the universe, but we don't really know what they are.
That's the humbling truth, yeah. Dark energy. It makes up something like 73% of the universe's total energy density. It's this stuff, with negative pressure that's causing the expansion to accelerate.
But what is it?
We don't know. Is it a property of space itself, like Einstein's cosmological constant? Is it some new kind of energy field? Its existence helps explain why the universe is flat and why the expansion is speeding up, but its fundamental nature is a complete mystery. And the theoretical attempts to calculate its value based on quantum physics are wildly off, like by 120 orders of magnitude off. It's maybe the biggest mismatch between theory and observation in all of physics.
Wow. Embarrassing, you might say.
Some physicists do call it that, yes. And then there's dark matter, making up about 27% of the energy density. We know it's there because we see its gravity pulling on stars and galaxies, bending light.
But we can't see it.
Nope. Doesn't emit, absorb, or reflect light. It's crucial for explaining how galaxies formed and hold together. But what is it? Is it some undiscovered particle? Multiple particles. We're searching hard, but haven't found it yet. And while the basic cold dark matter model works well overall, there are some lingering discrepancies on smaller scales, like the cuspy halo problem or the dwarf galaxy problem, which might hint that the story is more complex.
So basically 95% of the universe is made of stuff we can't see and don't understand. That's quite something. Now, you mentioned inflation solves the horizon and flatness problems. Let's just quickly revisit those.
Sure. The horizon problem is basically, how come the cosmic microwave background temperature is so incredibly uniform across the entire sky? Regions that appear on opposite sides of the sky today were, according to the standard Big Bang model without inflation, too far apart in the early universe to have ever exchanged heat or information. They shouldn't know to be the same temperature.
But inflation fixes that.
It does, quite elegantly.
Wow.
Inflation takes a tiny causally connected patch of the early universe and blows it up to be larger than the entire observable universe today. So everything we see did originate from a region that was small enough to reach thermal equilibrium.
Okay. And the flatness problem.
The flatness problem is about the geometry of space. Observations show the universe is extremely close to being geometrically flat. But according to general relativity, any initial curvature, however small, should have been massively amplified as the universe expanded. For the universe to be so close to flat today, it must have been unimaginably flat right at the beginning.
Which seems unlikely.
It seems like an incredible coincidence, requiring extreme fine-tuning of initial conditions. Inflation solves this too, because that exponential expansion stretches out any initial curvature. Just like blowing up a balloon makes a small patch on its surface look increasingly flat.
So inflation is like this essential prologue that sets the stage perfectly. Does it also deal with anything else? You mentioned something about magnetic monopoles.
Ah, yes, the magnetic monopoles problem. Some theories that try to unify the fundamental forces, grand unified theories, or GUTs, predict that exotic particles called magnetic monopoles, like an isolated north or south magnetic pole, should have been produced in huge numbers in the very hot early universe.
But we've never seen one.
Never. Not a single one, which was a big puzzle for those theories. Inflation provides a neat explanation. If monopoles were created before or during inflation, the subsequent massive expansion would have diluted their density so much that the chance of finding one in our observable universe today is practically zero. It essentially sweeps the problem under the cosmic rug, you could say.
It seems like the Big Bang model, especially with inflation, is incredibly powerful, but it also pushes the boundaries, leading to these deeper questions about origins and destiny. What about before the Big Bang? Can we even ask that?
That's the ultimate question, isn't it? And it's where we hit the limits of current physics. It's really important to stress. The Big Bang theory describes the evolution of the universe from an initial hot, dense state. It doesn't really describe the origin of that state itself.
So it starts the clock ticking, but doesn't explain how the clock got there.
Kinda, yeah. To understand the moment of the bang itself, or what might have come before, if before even makes sense, we almost certainly need a theory of quantum gravity, one that successfully merges general relativity and quantum mechanics. We don't have that yet.
But there are ideas, speculations.
Oh, plenty of fascinating speculative ideas. Maybe our universe arose from a quantum fluctuation in some pre-existing vacuum or space-time. Maybe it's part of a cycle of collapses and bangs. Some models propose an emergent universe that existed statically before starting to expand. There's the Hartle-Hawking no-boundary proposal, which suggests that time itself might become space-like near the beginning, so the question of before becomes meaningless, like asking what's north of the North Pole.
Mind-bending.
Definitely. Then there are ideas from string theory, like brane cosmology, where our universe might be a 3D brane floating in higher dimensions, and the Big Bang could have been caused by the collision of two such branes. Or maybe our Big Bang is just one event in a much larger multiverse undergoing eternal inflation, constantly spawning new bubble universes. These are all highly theoretical, pushing the boundaries of what we can even test.
So the beginning is fuzzy, maybe part of something bigger. What about the end? What's the universe's ultimate fate looking like these days?
Well, before we discovered dark energy and the accelerating expansion, There were basically two main possibilities, depending on the universe's overall density.
Right. Either collapse or endless expansion.
Exactly. If the density was high enough, gravity would eventually win, halt the expansion, and pull everything back together in a big crunch, possibly followed by another Big Bang in a cyclic model. If the density was too low, the universe would expand forever, getting colder, darker, and emptier, eventually reaching a state of maximum entropy called the Big Freeze, or heat death.
So which one is it looking like now?
With the discovery of accelerating expansion driven by dark energy, the Big Freeze scenario is definitely the frontrunner. The expansion seems set to continue forever and even accelerate.
What does that mean, practically?
It means galaxies will get further and further apart. Eventually, galaxies beyond our local group will recede so fast that their light will never reach us. Future observers will see an increasingly empty sky. Gravitationally bound structures like our galaxy will likely remain intact for an incredibly long time, but the universe between them will become vast and dark.
A rather lonely future.
It seems that way.
Yeah.
Now, there are even more exotic possibilities based on speculative ideas about dark energy. If dark energy gets stronger over time, what's called phantom dark energy, it could lead to a big rip.
A big rip. That sounds bad.
It does. In that scenario, the acceleration becomes so extreme it eventually overcomes gravity, then the electromagnetic force, then the nuclear forces, tearing apart galaxies, stars, planets, and ultimately even atoms themselves. But that's highly speculative. The Big Freeze is the standard prediction for now.
It's amazing how these scientific ideas inevitably touch on deeper philosophical interpretations, isn't it?
Absolutely inevitable. A theory about the origin and ultimate fate of everything naturally intersects with fundamental questions about existence, purpose, and meaning.
How do people usually react?
It varies hugely. Some people see the Big Bang, particularly the idea of a beginning to time and space as we know it, as strong evidence for a divine creator or a first cause. They might see the fine-tuning of physical constants needed for life as further evidence of design.
And the other side?
Others argue the opposite, that the Big Bang provides a naturalistic explanation for the universe's origins, describing emergence from physical laws, making the need for a creator superfluous. They might point to ideas like the multiverse to explain fine-tuning as a result of selection effects rather than design. The key point is that the scientific theory itself, the Big Bang model, describes the what and how, but it doesn't inherently prescribe the why. It's a scientific framework, and the philosophical or religious interpretations are layered on top of that by individuals and communities.
That's a really important distinction. Okay, before we finish, let's quickly tackle some common misconceptions. Things people often get wrong about the Big Bang. What's a big one?
Maybe the most common one is thinking the Big Bang explains the absolute origin of everything, energy, space, time from nothing.
But it doesn't.
Not really. As we discussed, it describes the evolution of the universe from a very specific, extremely hot and dense initial state. It tells us how that state expanded and cooled to become the universe we see today. It doesn't explain where that initial state itself came from or why there are laws of physics at all. That's still in the realm of quantum gravity and, well, maybe philosophy.
Right. It's the story after time zero, not necessarily at time zero or before. Okay, what else? The name itself, Big Bang, is a bit misleading, isn't it?
It really is. It conjures up this image of a giant bomb exploding in space, flinging matter outwards into a pre-existing void.
Yeah.
But that's completely wrong. The Big Bang was not an explosion in space. It was, and still is, an expansion of space itself, everywhere, all at once.
Like the raisin bread analogy.
It's exactly like the raisin bread analogy. The raisins, galaxies aren't flying through the dough, space. The dough itself is expanding, carrying the raisins with it. There's no center to the expansion, and it's not expanding into anything. Space itself is getting bigger.
Okay, expansion of space, not in space.
Mm-hmm.
Got it. And one last one, this idea about galaxies moving faster than light. That breaks physics, right?
Ah, yes, that often causes confusion. When Hubble's law says very distant galaxies are receding faster than light, it sounds like it violates Einstein's rule that nothing can travel through space faster than light.
Right.
But the key is that these galaxies are not traveling through space at that speed. It's the space between us and them that's expanding so rapidly, it carries them away from us faster than light can cross that growing distance. Their local velocity through their patch of space isn't faster than light. It's an effect of the overall expansion of space-time itself, which isn't bound by the speed limit for objects within space-time. So it's not a relativistic velocity in the usual sense.
That clears things up. It's the space stretching, not the galaxy speeding.
Exactly. So here's something to mull over as we wrap up. Consider this. If the universe is constantly expanding, and that expansion is accelerating thanks to dark energy, it means that more and more distant galaxies are constantly crossing an observational horizon, a point beyond which their light will never be able to reach us no matter how long we wait.
They're effectively disappearing from our view forever.
Right. So what does that imply for future generations of astronomers, maybe billions of years from now? Will they look out and see the same rich tapestry of galaxies we do? Or will their view of the cosmos have gradually faded, leaving them in an increasingly isolated, seemingly empty universe, perhaps unable to even deduce the Big Bang ever happened?
Wow, that's a profound thought, losing cosmic history over time. Okay, that brings us to the end of this deep dive. Thanks for listening. We really hope exploring the Big Bang has given you some amazing new ways to think about our cosmic origins. Now, we'd love to hear your thoughts in the comments on this. If time itself began with the Big Bang, what does it even mean to ask what came before it? Let us know, and please subscribe to the channel. It really helps more listeners find our deep dives. Thank you, and have an amazing day.